So this starts with us reviewing the two types of compounds. Now, you guys know the two types of compounds because we went through nomenclature, right? So remember, ionic, that's going to be a metal and a nonmetal. And covalent, that's going to be just nonmetals. But now we're getting a little more detail than we had before. In an ionic compound, there's an exchanging of electrons. That's what creates the ions, right? What always happens in an ionic compound is the metal gives an electron or electrons to the nonmetal. Every single time. That's what happens in a ionic compound is metals are giving electrons to the nonmetals. What does that do? Well, the metal becomes a positive cation and the nonmetal becomes a negative anion. So that's where we get these ions with the exchange. In covalent compounds, the electrons are shared, right? So this is where you can share two electrons, you can have a single bond, you could share four electrons, you can have a double bond, or you could share six electrons between two atoms, you could have a triple bond. So this is kind of big differences. So the way we draw ionic Lewis structures, totally different than covalent. Okay, here's the good news. This is like the opposite of nomenclature. Ionic Lewis structures are easy. The nomenclature was hard, right? Covalent Lewis structures are hard, but the nomenclature was easy. So it's like they're now flipped, with what's going on. So we're going to start with ionic Lewis structures. And we're going to talk about the strength of an ionic compound, its lattice energy, and all that stuff. These structures were developed by this beautiful man right here, G.N. Lewis. Love the dude, hate the picture. I hate the picture because he's in the lab, he's looking at crap above his eyes, and he's not wearing safety glasses. What is going on there, dude? I realized this was like a publicity, thing, but you got to wear safety glasses, man. If one of you did that, I'd be furious. So, this dude absolutely deserved the Nobel Prize. He should have got the Nobel Prize. He got passed over time and time and time again. It's kind of tragic. He ended up dying under some crazy circumstances, and they don't give out the Nobel Prize posthumously. And why would you care? Because you're dead. What's it matter anyway? I guess your family would get some money. But after his death, this was a big driving force for a lot of people saying, maybe we need to get rid of the Nobel Prize. Obviously, that hasn't happened because he died in 46. But the Nobel Prize is stupid. We should probably get rid of it. Anyway, he totally deserved one because he was the man. So let me share a periodic table. The way we do ionic Lewis structures is with what are called dot diagrams. Now, I don't do covalent Lewis structures with dot diagrams, although some people do, and you probably did in high school. I hate doing dot diagrams for covalents. We'll talk about that later. But for ionics, I think it works. For an ionic Lewis structure, or for any Lewis structure, the way this works is you're only interested in valence electrons. That's really like the interesting thing that Lewis brought to the party is he said, the electrons in the outer electron shell and the valence shell, they're the only ones that can make bonds. They're the ones that are going to interact with other things because they're on the outside. So Lewis essentially said, forget the core electrons. Let's just worry about the valence electrons. Only the valence electrons are going to be the ones that we should concern ourselves with. Now, remember, there is a shortcut to getting valence electrons. You number across the top 1 to 8, skipping the transition metals. So 1, 2, skip the transition metals. 3, you get the point, all the way to 8. Now, you can put dots around the elements, okay, to represent the elements' valence shell. These are called Lewis dot diagrams. Whoops. And again, I actually only like these dot diagrams for ionic structures. Okay, we'll talk about why. But for example, if I was going to do the Lewis dot diagram for, let's say, phosphorus. Phosphorus is part of nitrogen's family. So find nitrogen. Nitrogen's family has got 5 valence electrons. It's got 5 valence electrons. So phosphorus has got 5 valence electrons. Here's what Lewis said. Lewis said, imagine that there's a box around that symbol. The box isn't really there, but imagine it's there. You're going to put 1 electron on each face of the box before you double up. It's kind of like Hund's rule. So for phosphorus with 5 electrons, we're going to do 1, 2, 3, 4, and then I don't care which one you double up. I'll double up the bottom one 5. So that'd be the Lewis dot diagram for phosphorus. If I was going to do the Lewis dot diagram for chlorine, go ahead and find chlorine. Chlorine is a halogen, group 17. It's got 7 valence electrons. So we're going to do 1, 2, 3, 4, 5, 6, 7. I left that guy unpaired. You could have left the top unpaired. You could have left the right side, whatever, as long as you know you get 1 empty slot there, right, for chlorine. If you're going to do calcium, go ahead. Why don't you do the Lewis dot diagram for calcium? If you're going to do the Lewis dot diagram for calcium, calcium's got 2 valence electrons. So I don't care where you put them as long as you don't put them together. You could do left and top. You could do left and right. You could do bottom and right. Whatever. I don't care. Just kind of split them. Make sure they're not paired up because you got to put 1 on each face before you pair up. Okay. How do we do dot diagrams for ionic compounds? So that's dot diagrams for individual atoms. How do we do this for ionic compounds? Well, it's pretty cool. If you do the dot diagrams for an ionic compound, you can actually see what the electrons are doing to make that ionic bond. Here's how this works. We're going to start with sodium chloride. It's pretty easy. We're going to do the dot diagram for sodium. So sodium has got 1 dot. If you find sodium on the periodic table, neutral sodium, 1 valence electron. Now we're going to do the dot diagram for chlorine. If you find chlorine on the periodic table, chlorine has got 7 valence electrons. Got 7. So what's happening when you bring a sodium and a chloride together? When you bring sodium and chlorine together, boop, the sodium is going to give the electron to the chlorine, right? And these guys are both going to satisfy what is called the octet rule. The octet rule is the driving rule in Lewis structures. And the octet rule says everybody wants 8 electrons in their valence shell. So here's what happens. This is easy to see for chlorine. When sodium gives that electron to chlorine, it's now got 8. But then you say, wait a minute, how does sodium have 8? Here's how. If you look at the periodic table, when sodium gives away an electron, it's now backwards. It's now isoelectronic with neon, who has 8 valence electrons. Metals lose electrons and go backwards and become isoelectronic with the previous noble gas, whereas nonmetals gain electrons and go forwards and become isoelectronic with the next noble gas. So that's what's going on here. Now we are not done. Okay, this is like the show your work section. Now we need the like after, like what happens afterwards. Well, once sodium gives away an electron, no longer neutral, now it has a +1 charge. The chlorine has gained an electron. I'm gonna color code it. This is the electron that moves. I'm going to color code it, although now I got that marker I made that marker all kinds of dirty today. I'll do it in blue. I don't even know if that shows up or not, but that's a different color. That's blue. And the nonmetal, which has all the dots, what we do is we put brackets around that, and then we put the charge on the outside. Don't ask me why. I think it's meant to say, hey, the dots are on this guy. Right, and then we kind of write that. So this is what happened. This is actually, I like this. This is showing what the electrons are doing. In an ionic bond, the electrons go from the metal to the nonmetal. The metal becomes positively charged, becomes a cation. The nonmetal becomes negatively charged, becomes an anion. That's what we get here. Okay, this was a super easy one. Let's look at one that's a little more complicated. Let's do calcium bromide. Calcium bromide, of course, has the formula CaBr2. Calcium is plus 2, bromide is minus 1. You need 2 bromides to cancel that out. You're going to want to set this up like a calcium sandwich. So that's going to be bromine, calcium, bromine. And that's really going to be the first step in getting this thing right. I got 1 calcium and 2 bromines. So calcium goes in the middle, 2 bromines on each side, or 1 bromine on each side. Now we need to do the dot diagrams. Calcium, 2 dots. Boop, boop. I'm going to do left and right. You could have done top and bottom. You could have done left and top. This is not my first rodeo, so I'm going to do left and right. Bromine, 7 dots. So 1, 2, 3, 4, 5, 6, 7. I left a spot open over here on the left. You can probably see why. And then same thing here. 1, 2, 3, 4, 5, 6, 7. I left a spot over here open. I guess I'm sorry. That spot's open on the right. That guy's open on the left. What's going to happen? How can these 3 elements come together and make each other happy? Well, calcium going to give 1 electron to each bromine. And when it gives 1 electron to each bromine, what happens to the calcium? Well, the calcium just lost 2 electrons. So the calcium now has a plus 2 charge. And the bromines have now gained 1 electron each. So they now have a minus 1 charge each. There's our ionic Lewis structure for calcium bromide. I want to see the whole thing. Like on a test, if I asked you to do an ionic Lewis structure, I want to see, circling the dots that are moving, and I want to see what's left afterwards, because you're showing what's happening here. Why would a calcium and 2 bromines want to come together? A calcium and 2 bromines want to come together because calcium is looking to give away 2, but each bromine is only looking to take 1, and we end up with that. Cool. All right, I want you to try one. See if you can figure it out. I want you to try potassium oxide. Give that guy a shot. See if you can do it. Worst thing you could do is get it wrong. All right. This one's going to be an oxygen sandwich, right? So oxygen goes in the middle, and we're going to put a potassium on each side. So potassium's got 1 valence electron. We're going to do 1 dot for each potassium. We're going to do 6 dots for the oxygen. Now, not my first rodeo, as you could probably see. So I set this up very nicely. Okay, I did the 1 dot for this potassium on the right, 1 dot for this potassium on the left, and I left 2 open slots over here. So I singly occupied, and then I paired and paired. Now, you could have paired this guy up, whatever. You would just be moving, but I think it looks prettiest. And again, you certainly don't have to do exactly what I did. Okay, but I think it looks prettiest if we do one of these. Electrons going from the metal to the non-metal. We're left with an oxygen in the middle that's got a full octet. And these potassiums are rocking a plus 1 charge. Let's. Okay. Cool. Cool. You want to see how hard these get? Sure you do. All right, let's try this guy. This is as hard as an ionic compound gets. I'm going to walk you through this one. It's all about how you set it up. Let's do aluminum oxide. Aluminum oxide, Al2O3. This is a swap and dropper, and a swap and dropper. This was swapped and dropped, right? Aluminum's plus 3, oxygen's minus 2, so they swapped it and dropped it. Swap and dropper is the hardest to get. And it's all about how you set it up. And I like to call these molecules the Big Macs of molecules, right? Why do I call them the Big Macs of molecules? Well, it's 2 all beef patties, special sauce, right? Here's what's going on. It's like, if we think about the construction of a Big Mac, you got the bun, then you got a burger, then you got more bun, then you got another burger, then you got more bun, right? The bun are the oxygens, and the burger are the aluminums. It's like a Big Mac, man, right? So it's going to be like oxygen, aluminum, oxygen, aluminum, oxygen. That's how you got to set this thing up. Only I do it, left to right. So that's the key to the whole molecule here. So we're going to do an oxygen, aluminum, oxygen, aluminum, oxygen. Oxygen's got 6 electrons. 1, 2, 3, 4, 5, 6. Aluminum's got 3. 1, 2, 3. Oxygen's got 6. 1, 2, 3, 4, 5, 6. Aluminum's got 3. 1, 2, 3. Oxygen's got 6. 1, 2, 3, 4, 5, 6. So, what happens here? Watch. Aluminum gives 2 electrons to one of the oxygens and 1 electron to the guy in the middle. And then this aluminum gives 2 electrons to this oxygen and 1 electron to the guy in the middle. And what are we left with? Well, we are left with an oxygen with 8 electrons, and aluminum plus 3 in the middle, and oxygen here with 8 electrons, and aluminum plus 3 in the middle, and an oxygen over here with all 8 dots around it. And that's how you would do like aluminum oxide. Yo. All right. All right. We're doing good. We're doing good. Okay. Here we go. Let's get some theory here on ionic bonding. The strength of an ionic bond depends on 2 things. It depends on the magnitude of the charge. So how big is the charge on the ions? And it depends on the size of the ions. So how big are the ions? So the greater the charge, the stronger the ionic bond. And we call ionic bonds lattice energies because ions exist in a crystalline lattice, or ionic compounds exist as a crystalline lattice of ions. We call the smallest unit of an ionic compound a crystalline lattice. So that's why we call these the lattice energies, the amount of energy needed to break the, lattice, or to create, is how much energy is released when you create a lattice of ions. Anyway, so the greater the charge of the ions, the greater the lattice energy, the stronger the ionic bond, and the smaller the size of the ions, the stronger the ionic bond. Now, charge is way more important than size. The charge of the ions is way more important than size. But if it's a tie, like if both things have the same charge, then it will come down to size. So for example, if we look at calcium chloride versus sodium chloride, calcium chloride has a much larger lattice energy, 2,170, than sodium chloride, 787. Why is that? Calcium has a +2 charge, and chloride is -1. Whereas over here, sodium is +1, and chloride is -1. So the +2 charge on the calcium is bigger than the +1 charge on the sodium. So think about it like this. Those charges are like how strong the ions are pulling on the other ions. So if I have a greater charge, it's going to suck the other ion in and make it harder to separate the ions from one another. It has a higher lattice energy, or a stronger ionic bond. But what if so charge, more important than size. If I had, by the way, if I had calcium oxide up here, CaO, that would be even greater than calcium chloride. Why? Calcium's +2 and oxide's -2. So now I have a +2 -2 instead of a +2 -1. So calcium oxide would have an even higher lattice energy than 2,170. But what if it's a tie? So lithium chloride versus sodium chloride. Lithium chloride +1, -1. Sodium chloride +1, -1. So it's a tie for charge. Now it's going to come down to size. Because lithium is smaller than sodium, the ions can get closer together, and therefore it would be slightly harder to separate them. I'll show you what I mean, right? If we draw this, if you look on a periodic table, if you find lithium and you find sodium, you should see that they are both alkali metals. And you should see that obviously lithium way smaller than sodium. So lithium and chloride, these guys can get, if I go from the center of this nucleus to the center of that nucleus, those guys can get that close together, right? Okay, they can get a little closer together. Sodium now, bigger. Chloride, same size. I'm going to try and draw it the same size. Who knows? These guys now are further apart. That's a little further apart than this. Okay, I didn't do a great job there, I guess. My chloride, I think, got smaller. Okay, I'm going to exaggerate this. So here's my sodium. Further apart, further, closer, right? The smaller the ion, the closer they can get to one another. So is this, how big of an effect does this have? Not nearly as much as charge. If we look at the ionization energy, it's going to be a little harder to rip the lithiums and chlorides apart than the sodiums and chlorides, but not much harder, right? If you look at the data here, 829 kilojoules of energy to rip a mole of lithium chloride ions apart, and it would take almost 787 kilojoules of energy to rip a mole of sodium chloride. So lithium chloride is not that much stronger, right? You do the math, it's not really that much stronger than sodium chloride. Cool. So that's called lattice energy, right? A lot of times people in tests, they overlook that. There'll probably be some kind of question on lattice energy on the test. Make sure you know, like, so if I asked you to compare, for example, I'll put some up here. So, like, how about, like, who would have the greatest lattice energy? Who has the largest lattice energy? Oh, let's see. Let's do sodium bromide, magnesium bromide. Let's do I don't know, potassium bromide. Let's do magnesium oxide, sodium oxide. Let's compare those. Take a look at those five. Out of those five, who would have the largest ionization energy? Or lattice, or sorry, not ionization. Who would have the largest lattice energy? Who would be the strongest ionic compound? So let's look at this. And the first thing I do is I write the charges. So sodium's +1, bromide's -1. Magnesium's +2, bromide's -1. Potassium's +1, bromide's -1. Magnesium's +2, oxide's -2. Sodium's +1, oxide's -2. Magnesium oxide, folks, that's going to be your largest lattice energy. Why? It's a +2 -2. It's got the greatest magnitudes of charge, right? So that one would have the highest lattice energy. Cool.